Okay, welcome back to our last topic on this, what I call part 2 of this course, which is part 2 is about forces. And this is going to be our final topic to wrap up the part on forces. And this is a great topic, a great final topic to end this segment, this section of the course with, because for two reasons. Number one, this is one of the most interesting topics, certainly for the course itself, but also for all of physics. In some sense, my own research is to really try to understand how gravity works, because surprising to maybe some of you is we don't understand fully how gravity works. This is one of the oldest force that people study all the way back to Galileo and Newton, and 300 years later, we're still looking, and there's still new surprises on it. And I'll clarify what I mean a little bit later on. What we do understand very, very well, which is what we will study. And if the time permits, at the very end of this lecture, I'll also tell you what we do not understand very well and where does this law fails, right? And should that bother you, right? If you ever need to fly a spaceship into space, right? Do you need to worry that gravity suddenly does not behave how you expect it to behave? And we'll talk about that. When should you be worried? When should you not be? And when do we know very well how it works? And when do we, in what areas or what regime or what time do we know that we are not so sure? Okay. For a second reason, this is a good shift of gears. As I say, is we have done a lot of problems, right? We have the whole of last week was about solving problems after problem. So it starts to get a little dull of inclined planes and pendulums. Sure, now you know how steep you should park your car or you should not park your car. If you ever go up an inclined plane and put your car in park, you know how to calculate what is the maximum friction it can support, and you realize you should not drive up any slope steeper than that. Sure, and we learned about circular motions. That's all good, but a lot of problem solving. And now we'll shift gear a little bit to talk about something more conceptual in today and more theoretical. So this is also something that physics, some students find physics difficult, is from not recognizing the fact that I'm going to say it's probably not surprising to you that physics contains, whenever you take on a course of physics, there's two parts to it. You learn the concept, and then you learn how to solve problems, right? These two parts, to a lot of people's surprises, it really uses different sides of your brain, right? To understand conceptual, you need a lot of creativity, you need a lot of imagination. To understand how to solve problems, in a lot of sense, is about efficiency. What's the trick? What is the pattern? Okay, if I spot a pattern with certain types of problems, then I just need to apply the pattern, and that's about efficiency. Now, in some sense, learning a lot of students then focus on problem solving and forget about a concept, and it doesn't work for a reason. It's because if I tweak the question a little bit, it suddenly falls out of the pattern. And when you master the problem solving skills, it's all about efficiency and tricks and patterns. So you do a lot of similar types of problems. So the pattern arises, and now you can do a next problem very efficiently. But the problem is, the issue is if I tweak the problem a little bit, or if the situation is just a little bit different, right? The moment you step out of the classroom and you suddenly realize the world has friction or air resistance. And how are you going to do that? You will not be able to solve that. Or even if the exam question is a little bit different, if you don't understand where it comes from, it's no matter how efficient you are at solving one type of problem, you cannot handle any variation. So you do need the other side, which is understanding how to even come up with the pattern itself. How do you do that, right? So as you will notice in the exams and tests in this course, they're separated into two parts. There's section A, which is short answers, and section B, which is open response. And it's my attempt to sort of make it valuable for you to understand the concept, so that you can actually know how to solve it before you learn how to solve it efficiently, right? So all right, so now that you recognize there's two parts to physics, then another thing that will make your life in studying physics, because a lot of you will still go on for another 2 semesters or 2 quarters of physics class, another thing to make your life easier is know what you're learning. Whenever you sit down and take notes out of a physics class, sort of shift your mind, sort of prepare your mind to know that am I learning theory today, or am I learning a problem-solving skill? And if once you set your mind in the right mindset, it kind of makes the learning process a little bit more enjoyable, and you know what you're looking for, right? So today we're looking for imagination, we're looking for sort of a little bit of creative thinking, and a little bit of thinking outside the box, and thinking of how to build things together. How do we even come up with the law of gravity? How do we understand the world around us? And not so much about how do I set up a problem? If I see a problem, what is the 3 steps? Which is what usually I like to do is for problem solving is I try to summarize things into 3 steps. So like my brain is very simple. I couldn't handle more than 3 steps. So I try to see if I can spot sort of similar patterns in problem solving. So I can summarize into that. And when you're learning problem solving, that is kind of where I personally, that's how I was tackle it, right? And when you're learning concepts, there's a different way, a different side of thinking. Okay, anyway, so with that, we'll start with, we'll look at gravity, and it should be very curious to you that how this works, because it is one of the most mysterious force. Like I say, what do I mean by that is, what is a force? A force is a push or a pull. So we understand very well how contact forces work. I should say, it's very easy to imagine how contact forces work, right? If I punch my friend in the face, whether he likes it or not, he will know that he will experience a force, right? But if I do not touch my friend at all with no contact, and he still suddenly feels an acceleration, right? Remember, force is causal acceleration. Now that's very mysterious. On what magical world did I am able to cause that? So in some sense, gravity is one of the earliest non-contact force, and I think I may have alluded to that. In the whole world, we discover 4 types of non-contact forces, 4 fundamental non-contact forces in the whole universe, as far as we know, as of 2021. Okay, and that's it. Gravity is one of them. It's the earliest one that we notice. Right? How does it work? That's really a big question. That certainly bugged Newton. I don't think he even came up with a satisfactory answer himself. He fully admit he does not know how it worked, but he knows how to calculate it. He found out exactly how to calculate it, even though he couldn't figure out exactly why it is doing the way it is doing it. So he knows exactly the way it is doing it, but he doesn't know why. 200 years later, Einstein came along and has his theory of gravity, which is now known as the general theory of relativity, which not only explains how gravity works in the solar system, but also throughout the cosmos and throughout the universe. Very, very successful theory, and it finally has a good, solid attempt to answer how and why gravity works the way it is. Okay, so that is sort of the big picture, the context, and I want to motivate specifically on today's lesson with 2 questions that we will definitely be able to answer today. The first question is, what keeps the moon from falling down? If you think about it, we talked about weights, right? The Earth exerts a gravity, right? If you are on Earth, whether you're standing here, right, you certainly feel a weight. If there's an apple falling, the apple is a weight. Well, now there's the moon. So if you think, I'm sure every single kid, I will also bet that you have at one point in your life, you've thought about, what if there's the moon up there? What is keeping it up there? Why is it not falling down? What's doing it? Like we talked about Earth, what is weight? Weight is a force on an object by, right? Force is always on something by something. What is weight? Weight is a force, right, on the object by the Earth, right? It belongs to a non-contact force because it doesn't have to touch it. It still affects it. Now, does it affect the moon? So that's really the question, right? So you can phrase the question as, does the gravitational force of the Earth affect the moon? And if it doesn't, why not? Well, a lot of you know the answer is it does. But now the question is, what's keeping it from falling? Why does it not fall down? Every kid probably have asked that question, and it's just that we grow up and we have better things to do. But if you imagine yourself as a kid in mid-17th century England, you probably have nothing better to do. So you keep on thinking. For those of us who have nothing better to do, we keep thinking about this and we come up with a theory. So that's what our first question is what's keeping the moon from falling? right? And today we will be able to answer this, okay? Second question is a little bit more technical in the sense that does Newton's third law apply? Well, Newton already came up with his 3 laws of motion before he started pondering what's keeping the moon up there and not falling, crashing down to the Earth. So he has the Newton's third law, but now he is wondering, right? Because, all right, I think we know the answer that gravity does act on the moon, right? So let me write it in a more general form. So the force, so there's a force on the moon by Earth, right? We just need to figure out what's keeping it from falling down, if that is the net force, right? There's no other contact force. There's nothing else. It's not a column or a pillar that's holding it up. There's no tension that's holding the moon up, hanging from the ceiling, right? So that is the net force. That is all there is. So there must be an acceleration going downwards. Why is it not falling down, right? That's the first question. Second question is, well, we learned Newton's third law, which means there should be, if I flip this around, there should be an equal and opposite force. If this is pointing down, there should be an upwards force on what? Well, let's flip this around. It should be a force on the Earth by the moon. In fact, the Earth should also have a force on the Earth by the person. The person should drag the Earth up. Also, there's a force on the Earth by the apple, right? Also dragging, well, if this is the force on the apple by the Earth, there must be a force on the Earth by the apple. If you swap that around, that's what Newton's third law said, pulling it up. So the Earth is very busy. There's a lot of things pulling it up. Why is it not moving up, right? So let's ask. So we understand if there's a book on a table, with contact forces, we understand how this works, right? If there's a force on the, let's say the normal force here, right? So this is the normal force on the book by the table. And we understand the table experiences a normal force on the table by the book. All right, this is fine. All right, equal and opposite. All right, we understand. Now, does it hold for gravity? Because we have not talked about this. Whenever we talk about falling apples, we have not talked about does that happen, right? So the second question is, does the third law, right, holds? Okay, so these are the questions we'll answer, and yeah, we'll go and look at them in detail. Sorry, just want to add a quick clarification. What I mean here is, does the third law hold for gravity? That way, because we understand the third law holds for books, right? For anything with contact force, but now the question is, does it hold for gravity?